Welcome to our last session this morning at the Digital WE Days. My name is Doreen Schäfer and I will moderate this session. Next to me are Markus Haepe and Antwi and Nimo, who are both design engineers for the product area Power Transformers and Custom Magnetics. This morning they will present transformer safety updates on IEC 61558 standard. So, let's see what you have. The stage is yours.
Thank you very much. Thank you. I am here with my colleague, Markus Haepe. Markus is a design engineer here at the Custom Magnetics Division of Worth Electronics, and he has several experience designing custom magnetics, as well as he is a safety expert in our division. So, Markus, will you want to say a few words?
Yeah, welcome, Antwi. Antwi Nimo is also my colleague, design engineer in the Midcom group, and he's also a safety expert and has many experience in transformer design. And yeah, we will start with Antwi with the presentation now and have a lot of fun.
Okay, thank you, Markus. So, transformer standards and the approval process is not so straightforward for most of our customers. So it is not always very clear the level of safety that one needs for his or her application at the start of the project. So it becomes very complicated, as well as if you even establish what you need, navigating the standards and the requirements of the standard is always not straightforward. So this is why we are here to support you and also to guide you in your design process. So we are the experts that can really help you and guide you so that you don't have problems back at the production stage when you have to go and approve your standard. So you can count on us to be a reliable partner in your design process in terms of safety and its approval. Now let's look at what we will present this morning. So we will talk about transformer safety in general, what is safety, how you can achieve it, the concept of safety, and then we will talk about how to achieve safety according to the IEC 61558-1 standard. And then we will present some practical construction examples. And then last but not the least, we will be available for questions and some discussions. So what is the 61558 standard? So because transformers are safety critical components, there are standards that govern how you can design a transformer. So there are, for example, the safety standard 62368, which is a device standard or a product standard for audio, video, and ICT equipment. We have another standard like 6061 for medical applications. And then we have the 61010, for example, for lab control and measurement devices. So there are several other standards that govern safety critical components like a transformer. And then we have the 61558 standard. This is the general safety standard for transformers. So it's not only about the device or the end application, but the 61558 specifically defines the requirements for designing transformers. And the -2-16 specifically also writes the requirements for transformers that are used in switch mode power supplies. So this is a little bit about the 61558 standard. Now let's look at transformer safety. What are the factors that affect transformer safety? So there are several factors, but we categorize these into 4 cardinal factors. The first one is mechanical effect or mechanical factors. So you have things like the bobbin material, the tape that you use, even the terminal, and the shape of your transformer or affects the safety of the transformer. Then we have environmental factors, like where the transformer will be deployed. So if the transformer is deployed in, for example, a clean room, it will have a different safety level as when it is deployed, for example, in an outside environment where it is subject to rain, sunshine, tender strike, and so on and so forth. We also have thermal effects. So these days, there are more and more requirements to go small, as well as packing a lot of power, energy density into this small volume. And because of this, thermal management is also a very big topic. And the thermals also affect the safety of the transformer. So if you select components that are unable to withstand the temperature at which they are going to be operated, then the device will not be safe and it can break down already through these temperature effects. And then we have electrical factors, like how much voltage and current that the device will see will also affect the safety of the device. So these are the 4 cardinal principles that affect transformer safety. And the talk will focus more on the electrical. So we will not go deep into thermal or environmental effects, but it will focus mainly on the thermal effects. Now let's look at the safety. So there are several levels of safety, as I already introduced. One is functional insulation. So the functional insulation is only necessary for the correct functioning of the device. So if you design a device based on only the normal operating conditions, then it is functional isolation. Then we have basic insulation. So the basic insulation is insulation applied to live parts to provide protection against electrical shock in the absence of any equipment safeguard. So if you introduce a level of safety in addition to the normal operating conditions, then you can call that basic insulation. Then we have supplementary insulation. So supplementary insulation is additional insulation measures applied on top of the basic. So this is one step ahead to even make your component more secure or more sicher. So if you do this, then we call it supplementary insulation. And then we have double and reinforced. So double means the combination of basic insulation and supplementary insulation. So if you put, for example, basic insulation in one aspect of your circuit and then supplementary insulation on the other aspect of your circuit, we call it double insulation. And then we have also reinforced insulation. Reinforced insulation is applying a level of safety equivalent to both basic and supplementary combined into one circuit. So you don't separate the basic and supplementary into the circuits, but you apply the safety equivalent to the combination of the two in one circuit, then we call it reinforced safety. Now let's look at the various components in terms of wires that you can use to achieve this basic. So here we have a special wire which is used to achieve the safety called insulated wire, and this picture is taken from Rubadu. So if you see in the middle, you will have here your copper, and around it you have, let's call it a single layer of insulation. So just for argument's sake, I will call it a single layer of insulation. For supplementary, again, you will have your copper, and then you have a double layer of insulation. So in the picture, you have a white layer of insulation, and then you have a blue layer of insulation. And then we have the reinforced, which consists of 3 layers of insulation. So the reinforced will have the copper in the middle, and then you have the white, the gray, as well as the gray. So you have 3 levels of insulation to provide more safety. According to the 61558, you can also achieve safety by using a specialized type of wire, which is called fully insulated wire. And the fully insulated wire is what we are showing here. This picture is from Electrisolar. It's a company which manufactures wires. And it is also based on the copper and then the insulation layers realized with enamel. And these insulation layers are applied homogenetically so that there are no pinholes in the insulation layer. And through this approach, you can also achieve basic, supplementary, or reinforced insulation. And this wire can be used according to the 61558 to achieve levels of safety, as we already presented. Now let's look at overvoltage category. So the concept of overvoltage is what I showed in the beginning of my talk. Like if you have, for example, a device being deployed in the outside and a device being deployed, for example, in a clean room, the device which is deployed outside will be subject to more fault conditions, for example, like surges, like tender strikes, and so on and so forth. And this increases its overvoltage category because there is the propensity for the device to see more overvoltages. And this is what we try to depict here in the building. So from the main service point to your house, you will have, for example, the watt-hour meter and the main fuse boxes. Normally, devices that go into these sections of the house will have so-called overvoltage category 4, which is a very high level of overvoltage because it can be subject to a lot of fault conditions or noises in terms of voltages. And then we have overvoltage category 3. These are, for example, light switches, distribution panel, and socket outlets. And this is a little bit lower, but it can still be subjected to higher fault conditions. And then we have pluggable equipment. These are like our plugs and our devices like the monitor and so on and so forth. These are categorized into overvoltage category 2. And then we have devices that we can hold normally, for example, like the mouse. These are normally categorized as overvoltage category 1. Now, I will also like to introduce the concept of clearance and creepage, because when you have these overvoltages, what happens is that these overvoltages can creep or they can short circuit into other circuits. Because we've all seen when we accumulate a lot of electrostatic charges, when we have, for example, synthetic fabric, and then when we go close to another device, you will see an electrostatic discharge. It's the same concept that happens when you have a device which is subject to a lot of overvoltage. And this concept, we call it clearance and the creepages that you need to separate the circuit such that such short or such Durchschlag or such breakage, yes, will not happen. So here, the clearance is how much distance one needs through air between one circuit and the other, such that the fault condition will not break through into the other circuit. So this is the definition of clearance, as you can see in the red line. And then another definition is the creepage, and the creepage is the distance along the insulation surface that you need to separate the various circuits from each other such that you can prevent the breakdown of the overvoltages from going from one circuit into the other. So that is the concept or the definition of creepage and clearance, which is normally used in the safety world. Now let's look at how you can measure the working voltage. So if you have, for example, a transformer, and the transformer is subjected to a lot of voltages and currents, there is what we call the working voltage. It is the highest voltage across the insulation. And this picture here is taken from VDE. It's an approval agency that certify components like transformers. And it depicts here how one can measure accurately the working voltage. So you have here a transformer, and then you have here the input side and the output side. And the working voltage is the differential voltage between the input and the output reference to, for example, ground. So this is how one can measure the working voltage. Now I will show you a tool that we use internally here at the custom divisions at Worth to calculate how much creepage and clearances that you need. So I'm going to use, obviously, here the 61558 as an example. So here you have also the electrical factors as I presented earlier. You have the environmental factors as, for example, the pollution degree, and then you have the mechanical factors and so on and so forth. So I will step out of the presentation mode and show you the tool. So here is the tool. Here is the 61558 standard. Here you can put in the number or the component number that you are working on. And here is the working voltage that I showed earlier. So for example, the default here is 265, but I can change it to, for example, 400 volts. And then here is the peak. If I keep, for example, the frequency of the device at 100, and I select material group 3, and then the reinforced level, then I need 8 millimeters of creepage, for example. Here, if I put, for example, 500, then as you can see here, I need 10 millimeters of creepage. So this is the tool that we use internally to dimension how much creepage and clearance that we need. For example, if I also change to basic, then you can see instead of 10, then I need 5 millimeters of creepage. So this is a tool that we use to calculate the basic and the supplementary as well as the reinforced distances that we need for the transformers. Okay. So now let's look at how we can achieve safety. So this is the point where I will hand over to my colleague Markus, and Markus will take you through the second half of this talk. Markus, please.
Many thanks, Antwi, for your introduction and explaining. And I will show you how to achieve safety according to IEC 61558. I have some examples of reinforced insulation using FIW, and we can see here the core. Oh, wait, you can see here the core and the red lines here between core and the windings, and between the windings itself. The red lines are barriers which are designed for basic insulation, and they need to withstand the requirements of basic insulation. And you can see here primary is enameled wire, and I have a picture that you can see it directly, and the secondary is a fully insulated wire. And with this construction, is normally a standard construction, we can get a reinforced design like Antwi explained before. Another solution could be that you have on primary side the basic insulated FIW, and on secondary side also the basic insulated FIW. You can see here with the picture it's the same wire, same construction, And in the end, with this, we have the double insulation, and we get also double or reinforced insulation for this construction. We have many different constructions in the standard, in the 61558 explained, but I can show only some of them because it takes too long time to show everything. So I will show you now the design with the toroid core. You can see here in the middle there's the toroid, and it is written that the toroid needs a coating for basic insulation for the requirements of the safety. And this is not because of safety between the core and the windings. It is more a mechanical separation to save the wire, that the wire is not damaged when we wound it directly on the toroid. You can see primary side again an enameled wire, and secondary side, in this case, a triple insulated wire, the same picture as Antwi showed before, with the copper in the middle and 3 layers of isolation on top. So the next design I want to show is primary side with the basic insulated, fully insulated wire, and secondary side with the reinforced fully insulated wire. The toroid is again need to be coated with the basic insulation because of the mechanic stress of the wire and the core. And you can see the wire itself looks the same, but we have a table. We have to choose with the 61558 with the high voltage level the right FIW and the diameter and the grade of the FIW, like FIW 4 or 5 or 6, is needed to get the basic or the reinforced insulated. The next construction we have is with the EE core. Normally with the EE core we have no directly windings on the core. We take a bobbin or a coil former, and this is designed to withstand the basic insulation between core and the windings. You can see the primary winding is basic insulated wire, like here written, and you can see, like Antwi showed us before, the wire with only one coating, and the secondary wire is a reinforced wire, like shown before, with 3 layers of insulation. Another way to get the same construction with reinforced could be with FIW. We have changed the primary to reinforced insulated FIW and the secondary also to a reinforced insulated FIW. With this case, we have again the same wire on both sides for the high voltage requirements, and we need also a bobbin to separate the windings from the core, and in the end the isolation itself needs to isolate the windings internally. These were some practical constructions I want to show how we can use the showed designs before, and in this case we have different solutions how to realize the design with safety. The first is to use a margin or a shave tape to get the right creepage and clearances, which Antwi showed us we calculate for our design. In this case, we can see here it is a bobbin chosen, which is designed for a longer distance because the margin or shave tape is directly realized with the plastic in the coil former itself. You can see here in this picture the first winding needs no tape, left and right side, because it is included in the coil former, and all the other windings on top, you can see here it is designed with shave tape. In these pictures you can see directly this coil former in real design. You can see here the barrier left and right side directly designed in the coil former, and in the middle you can see the windings. On top we bring normally 1 or 2 layers of tape to realize the separation to the other windings, and on top you can see we have to bring the shaved tape left and right side with a special tape to realize the distance in the next layer, and then we wound directly the winding in the middle of the reduced chamber. Another way to realize increased creepage and clearance will be to use extended rail design. In this case we have a bobbin with horizontal extended rail on one side. You can see it here, and we use standard triple insulated wire on this side to realize the safety. We have to take care in this case of burn back, because when we solder the wire here on this area, it could happen that the wire isolation is damaged in a special way, and in the end we have creepage distance which is a little bit reduced because of this distances. So what can we do in this case? We can also take a margin tape or shave tape to increase the creepage and clearance. Here we can see here's the tape, and then we increase the distance from pin or from the isolation, the damaged isolated wire to the primary winding. Another solution could be a 2-section bobbin. We have here 2 designs in the same bobbin. You can see on the left side the design is very full. On the right side it is half of the winding chamber used. So you can see that the design itself on the left side has lower creepage and clearances, and on the right side the distances are much bigger. In this picture here you can see it directly. The way around this barrier is much longer as in this picture. Mm-hmm. Yeah, I have some examples to show you how big could be design for safety. You can see here a very, very small toroid design with an extended rail, and with this design we could realize a safety design for the electrical requirements, and you can see it is very, very small against this coin. Another design, also a toroid but much bigger, could be that we take a kind of plastic, a cap around the core, and we can bring in the middle also a kind of plastic or something else to be sure that both windings are not able to touch and have the needed creepage and clearances between these both windings. We have also EE cores, and the design you can see here on top. It is with a very big distance between these both windings, so the barrier in the middle is very big. We have a cap here around the bobbin, so the core itself is far away from the winding and far away from the pins here, because the cap is also around the pins and over the core, and therefore we can design a very big creepage and clearance. And last but not least, we could also say we need a very small part, but the requirements are too high for this. Then we can choose the method to pot the part itself. Then we get a good part which is able to withstand all the electrical parameters we have to withstand. And in the end, the clearance is not needed because it is potted. There is no air around. And we need, in the end, a reduced creepage distance. Or if you need much more smaller parts, we can also reduce to the minimum is distance through the insulation, like the 61558 gave us. Mm-hmm. Yeah, we have in the 61558-1 and 61558-2-16 some news and updates. We have to test the partial discharge. It is a type test for each transformer, but please take care of this point because in the end, in the 61558-2-16, it is more or less written that all transformers needs to test it, and in the -1 there's written that all transformers with triple insulated wire or FIW wire with working voltage, peak working voltage higher than 750 volt needs to be tested. So please take care and check with your test lab. The FIW dielectric voltage requirements are reduced now, and the clearance distance calculated with the rated supply voltage. In the past, the clearance was also calculated with the working voltage. Yeah, overvoltage categories has been added. That is main important thing for us, I think, because in the old version we had only the category 3. So in the end, we were not able to choose or to reduce the creepage and clearances because of the categories. Mm-hmm. Yeah, last point is the frequency dependence on creepage. It is also included now in the 61558, and therefore we have to take care of all these special points that we get a good design in the end. Yeah, many thanks for your attention, and many thanks, Antwi.
Thank you, Markus.
That was our presentation, and now we are here to answer your questions. And
here. So this one is from Dietmar. Is it possible to get the Excel tool safety calculator?
Unfortunately, it's not released for the public. It's an internal controlled tool that we use for our customers, so it is not published yet for the public.
All right, thank you very much. So I guess that also wraps up the next question from Nadia. Is this tool an open source?
No, it is an internally an internally controlled document, yes.
Perfect. Thank you very much. So here's a question from Herbert. What are the main changes in the new standard 61558?
Yeah, the main changes we showed in the last slide. The main changes are in the partial discharge and how to handle it. In the past, we don't need it to measure it with including the FIW. It was needed to test with the FIW, and now we have to test it with FIW, triple insulated wire, and in the end, with the new -2-16, you have to check, maybe you have to do this test also for all the other designs you have. Yeah. In the end, clearance distances are calculated with the rated supply voltage now, and this is the main important thing, and the overvoltage categories. Yeah. The frequency dependence on creepage most of the time is not so interested because the frequency is low enough in the normal designs that it doesn't matter. But in the end, take care of this.
Perfect. Thanks for making that clear for Herbert. Mm-hmm. So I'm going to switch to the next question. It's from Tim. And he is wondering, is it possible to use FIW for the UL?
Yes, it is possible. Different standards take the FIW also in the UL standards. So it is not a general information you have to check, because it depends which standard you have to follow.
Yes.
Nothing to add?
Yeah, I think my colleague said it all. So
Perfect.
it is generally acceptable, but you have to check with your approval house.
Thank you very much, the both of you. So we still have a few minutes left, so we can move on to the next question. Oh, I hope I pronounced the name right. I think this question is from Chin Hui. Is it possible to have basic reinforced insulation without using FIW by keeping the minimum creepage and clearance?
Yes, it is possible. It's a question. FIW is a special magnet wire for high isolation, but you can also realize a design without FIW and without a triple insulated wire. Then you need the right distances and the thickness of the tapes you use. Then you can also use in all windings magnet wire, and you need the right margin or shave tape to realize all the distances. Most of the time, then you need also tubing like silicone or something else.
Perfect, thank you very much. Many questions for you today.
I don't know. We are happy to support.
Yeah, you're doing a good job. So let's move on to the next question from Marian. It's a longer one, so I will keep it here so you can read it as well. According to your slide, okay, for IEC 61558-216, compliant transformer, is working voltage is depend on peak voltage observed during SMPS MOSFET turn off. So it is depend on application, not mains voltage.
You are in the end.
The working voltage.
Yeah, the working voltage is over the isolation of the transformer, and this is measured in a special way. You have some information from VDE, for example. They have a special sheet where you can see how to measure and how long you have to measure it and how you have to set up your measurement device. So in the end, it depends on the input voltage, yes, but in the end, it is only the voltage measured across the isolation. So if you have a higher input voltage, normally you can say the working voltage in the end is also higher.
Yes.
Perfect. Thank you, Ab, for this enlightening answer. It was great. So there's another question from Nadia. Oops. Do the needed distances change if the trafo is encapsulated? If yes, is the encapsulating material plays also a role here?
Yes. So if you are able to encapsulate the windings, then in some cases you have the possibility to reduce the pollution degree. Mm-hmm. And then your creepage and clearance distances will be much shorter. Also, if you do a potting, then you have the possibility to reduce the creepage and clearance distance inside, and then possibly the creepage will be only from your terminal to the terminal. So it all depends on the construction. But in general, encapsulation can be used to realize a shorter creepage distance.
Thank you very much for explaining it so well and making it clear for us. So, with a look at the time, I say we have one last question left that we can answer here. So this one is from Karen. Does having a bobbin full of wires versus having a bobbin without with only a few wires change the creepage of clearance distance, like the example in page 22?
Yes. We can show again.
Yes, we can say yes. The construction with the two-section bobbin here, you can see when you have less number of turns or less number of windings in the construction, the height is, or the chamber is not so full in the end, and the distance over the barrier here is much longer. In the end, this design is done with the magnet wire. So the distance from this side and this side is big enough. The only way, or the shortest way, is here over the barrier, or directly when you mount the core directly to the core. But you have different solutions to increase the distances if you have a special cap which fits in the middle, or over the complete design that the core is more or less isolated from all the open connections.
Thank you very much, Markus. I know that we didn't answer all of your questions, but don't worry, Markus and Ninat will answer them afterwards via email. So if you still have some questions left, feel free to enter them into our chat. Also, a huge thank you to the both of you. You did a great presentation. And I have some good news for everyone who is interested in a topic. This afternoon, we have another session coming up from Aldo de Michel called Transformer Design and Midcom Capabilities. I'm sorry. It's this afternoon at 2:30 p.m. So feel free to register now. See you next time.
Thank you very much.
Thank you. Bye.
Bye-bye.